Hi, my name is Nima and I'm going to be presenting our paper on temporal performance modeling of serverless computing platforms. I'm a PhD student at the University of Alberta, and the other author of this paper is Dr. Hamzeh Khazaei, my supervisor and professor at York University. And all of the research for this paper has been done in PAC's lab in York University. You can also find the references to our paper at the bottom left of the screen. So today we're going to talk about, have an introduction to the work that we've done, and then we will talk about the system that is modeled by a performance model, and then we'll go through the process of analytical modeling of our approach for analytical modeling, and then we will see the experiments validating our results, and we will conclude the talk then. So serverless computing is the newest paradigm in cloud computing, and in this paradigm, the runtime operation and management is completely delegated to the serverless provider. And this basically reduces the overhead for software owner and basically allows the service provider to do all of the provisioning and scaling of resources tasks. Software is developed in this paradigm by writing functions, and the functions have well-defined interfaces and are deployed separately. So a normal developer workflow in serverless computing platform happens like this. You upload your code to AWS Lambda or whatever your service provider is, and then you set up triggers or events that cause the execution of your code, and then AWS Lambda or your service provider will execute the code only when those triggers happen, and you only have to pay for the resources that you actually use. And right now, service providers all have a best effort performance guarantee. So basically, you don't have performance guarantees, and using analytical models, we can improve the current generation of service platforms in a number of ways. We can ensure the quality of service. We can improve the performance metrics. We can predict or optimize the infrastructure costs, and we can move from best effort basis to performance guarantees. It can benefit both service provider, and the application developer. So for system description, first have to define function states. So the tiny servers that will run your code in the cloud are called function instances, and those function instances can have three states. They can be in the initialization state, which is when the function is doing initialization tasks, creating containers, downloading code, making data connections to databases, or anything necessary to prepare the system. Then after some time, when the instance is ready, it starts processing a new request, and it goes to the running state, and after some time, when the process is done processing, it will be in the idle state, which is when we have provision capacity for future requests. So if we have enough capacity to handle a new request, that request will be a warm start request, which means we have an idle instance that will start processing that request right away. But if we don't have enough provision capacity, that request is going to have to be a cold start request, which means it has to wait for a new function instance to be initialized and then start processing, which usually takes longer than warm start requests. So to talk about auto-scaling, we have to look at both scaling out and scaling in actions. In the scaling out actions, we have a warm pool of resources, and if we don't have enough capacity to handle the new request coming in, that request will be blocked by the warm pool, and it will cause a cold start if we have not reached the maximum concurrency level. And when it causes a cold start, it will cause the creation of a new function instance that will be added later on to our pool of resources. Well, so that's for scaling out actions when we want to add new resources to our pool. For scaling in, we have to take a look at the life cycle of one function instance. And so a function instance is created, it processes some requests, and then after processing its last request is done, which takes usually about 1/mu. It will be kept warm for some time, which we call expiration threshold. And afterwards it will be expired and terminated, and the resources that it is consuming will be released by the serverless provider. So to model such system, we used a Markov chain, and each state represents the number of function instances that we have in our warm pool. So to figure out the rate of adding new instances to that pool, or expiring existing instances and releasing those instances from the pool, we have to take a look at those actions and calculate the rates for which we can find the detail in our paper. And so for each of these states, we can actually calculate probability of rejection, probability of cold start, and average response time, and we can actually calculate the mean number of instances in the warm pool that are in the running or idle state. And from those, we can calculate the utilization or wasted capacity in our platform. And all predictions using our temporal model can be found in a time-bounded fashion. So for example, we can answer questions like, what happens to my quality of service in the next 5 minutes? So for our experimental validation, we performed all of our experiments on AWS Lambda. We use Python 3.6 runtime with 128 megs of RAM for each function instance. We use a mixture of CPU and IO intensive tasks. And the client was a virtual machine that has single digit and fast connectivity to AWS servers. And we communicated directly with the AWS API, AWS Lambda APIs, so that we don't have any intermediate interfaces like API gateway, so that their performance does not affect our results. The predictions are made 5 minutes into the future, and we're assuming an Oracle pattern, request pattern prediction. So this is the request pattern that we applied to the serverless platform. And it takes about 1 hour to apply this pattern, and we performed this experiment 10 times, and we only report the average values of those 10 executions here. This is the cold start probability throughout that pattern, and as you can see, the experimental results line up very good with our performance model predictions, which were 5 minutes in advance. So these can predict also the average response time of the system in the next few minutes. This is the utilization of the system. So what ratio of function instances were actually being used by the provider at each moment in time. And basically using this value, the provider can find out how good they are using the resources deployed for each function. So in conclusion, we developed an accurate and tractable analytical performance model here. It gives us the ability to predict important performance or cost metrics, and it can predict quality of service. It can benefit service providers in the way to make them able to predict quality of service under different workloads. On deployment time, they can be used in the management system to prevent performance degradation. And they can also be used useful to application developers. They can predict how the system will react in different scenarios, what the capacity of the system and limitations of their system is. And they can optimize their memory configuration to occur minimal cost that satisfies their performance needs. And it can also be leveraged in the management system, so service provider can warm up function instances to prevent SLA violations. So in summary, we developed a performance model for a system that was described in our system description phase. And we developed a performance model based on that, calculated all of the rates, and we performed temporal predictions. And so in our experiments, which was applying this request pattern, we calculated several key performance metrics for our services. And you can see the cold start probability here. And using those calculated service QoS characteristics, you can actually predict the quality of service in the next few minutes, and that can be used to improve the quality of service of in-service computing platforms. You can actually go through more details of our work in our websites, or you can also check out my Twitter account. Thank you very much.